What does Neptune hide? Today, we head to the outskirts of the solar system, a frozen realm swept by the fastest winds in the solar system. Neptune, more than a planet, a blue ghost in the abyss. From the first mathematical intuitions to the blurry images from probes, it eludes, it intrigues, it haunts. What do we really know about this distant world? And why, in the vastness of the void, have our eyes turned toward it? But before we embark on a new adventure, don't forget to like the video and subscribe to the channel to ensure you don't miss anything. Thank you, and have a good trip. September 23rd, 1846, marks a major turning point in the history of astronomy. On this day, the existence of a new planet is confirmed, even though no telescope has yet clearly identified it before. Europe is experiencing a period of scientific excitement. For several years, astronomers have been puzzling over mysterious perturbations in the orbit of Uranus discovered in 1781. Meticulous calculations reveal that its trajectory deviates from the predictions established by the laws of celestial motion. Yet, since Kepler and Newton, the sky seems to obey well-defined rules. Why does Uranus seem to stray from its expected path? Some scientists believe that an invisible force or an unknown object is at work, disrupting its course. Nothing is certain yet, but two researchers managed to calculate the position of a hypothetical celestial body that might explain these anomalies. This calculation work is carried out simultaneously, at a distance, by Urbain Le Verrier, a French mathematician and astronomer, and John Couch Adams, a British mathematician. Separated by more than 1,000 kilometers or 621 miles, they communicate little, but each develops comparable methods to locate this unknown body. They start from the principle that universal gravitation cannot be questioned by a few anomalies. They conclude that another planet exerts an influence on Uranus, explaining its irregular trajectory. Le Verrier, more followed in the media, sends his findings to several observatories, indicating precisely where to point their instruments. He provides detailed celestial coordinates and justifies his approach, claiming that such a massive object cannot go unnoticed if observed in the right place, at the right time. Adams reaches similar conclusions, but he does not immediately obtain the support needed to validate his prediction. History will therefore mainly remember the name of Le Verrier, although both worked in concert without knowing each other. On the night of September 23rd, Johann Galle, an astronomer at the Berlin Observatory, discovers this planet exactly at the location indicated by Le Verrier. With his assistant Heinrich d'Arrest, he uses the received coordinates. The idea of finding an unknown planet by scanning a narrow portion of the sky, guided by calculations, seems improbable. Yet, as soon as the telescope is aimed, they spot a bright point that does not correspond to any known star. Observing it over time, they detect a slight movement, characteristic of a planet. This spectacular discovery confirms the role of mathematics in space research and marks this night of September 23rd, 1846, in the scientific annals as the moment when the 8th planet of the solar system was officially observed. Soon after, the question of what to name it arises. Several suggestions emerge, drawn from both mythology and the scholarly world. But the dominant tradition remains that of Greco-Roman deities. Mercury, Venus, Earth, Mars, Jupiter, and Saturn already form a well-established lineage. Uranus has imposed itself over time. For this distant, bluish planet, the name Neptune, Roman god of the seas, is ultimately chosen. The choice is validated by an international consensus, everyone understanding the importance of remaining faithful to this cultural heritage. In the ancient imagination, Neptune reigns over the oceans and their infinite expanses, an image that evokes the grandeur and remoteness of this new celestial body. The name Neptune thus carries a strong symbolic significance. The oceans, by analogy, remind us of the vastness of space still unexplored, sometimes compared to a celestial sea. In 1846, almost nothing is known about this planet, but mythology gives it an identity. The international agreement reflects a common desire to better understand the solar system. Astronomy already is establishing itself as a collaborative science. Despite their rivalries, European observatories all acknowledge having contributed to the validation of a theory that seemed daring. One might think the story ends at this date. However, an unexpected fact resurfaces much later. Galileo Galilei, the famous Italian astronomer, had already observed this region of the sky 2.5 centuries earlier. In 1612, while studying the satellites of Jupiter, he noticed a bright spot that he interpreted as a star. His attention being focused on the motion of Jupiter's moons, he did not question this object further. By examining his drawings today, we understand that this alleged star corresponded to the exact position of Neptune. Without knowing it, Galileo had seen the planet before anyone else. However, he did not note its movement, and his instruments, still rudimentary, did not allow for detecting this type of variation. At the time, the idea of a planet beyond Saturn didn't even exist. Neptune thus went unnoticed, waiting 2 centuries to be identified as such. Why did this point not intrigue him more? Perhaps he thought it was an error or a star still poorly catalogued. The celestial charts of the early 17th century remained incomplete. Even a mind as brilliant as his could miss the significance of such a clue, especially as he was concentrating on other scientific revolutions. In his notes, Galileo expresses no doubt on this point. Without repeated measurements of the movement, it was almost impossible to guess the true nature of the object. It is only in the 20th century, through the confrontation of his sketches with modern data, that researchers realize he had, unknowingly, drawn Neptune. All of this underscores how complex the process of an astronomical discovery is. You need to prove that an object moves, and that it logically explains the observed anomalies in the trajectories of other celestial bodies. The prediction of Neptune through the perturbations of Uranus remains one of the greatest successes of Newtonian gravitation. It is a striking example of the combined power of theory and observation. First, an anomaly, then a hypothesis, finally an observation that confirms it. This success encourages the use of mathematics to locate invisible bodies, proving that you can detect a celestial body even before seeing it. After 1846, the astronomical community hastens to analyze Neptune. Attempts are made to measure its size, to study its role in the organization of the solar system. But what interests us here is that precise moment when, in Berlin, a mathematical prediction becomes reality. In a few hours, a hypothesis turns into a discovery. Adams receives confirmation that his calculations match the observation, even though Leverrier, having acted faster, gains more recognition. This is why the discovery is often associated with Leverrier and Gall, while Adams remains in the background. Following the official announcement of Neptune's discovery in September 1846, the scientific community's attention immediately turns to the first concrete measurements regarding this newcomer to our solar system. At that time, astronomers remain astounded that Neptune had been predicted by calculations before even being seen through a telescope. A crucial question then arises: how to accurately determine the size and mass of a body so distant? From the end of 1846 until the dawn of the 20th century, these studies intensify and allow essential data about the blue planet to be acquired. It is also during this period that a major discovery takes place, that of its largest satellite, now known as Triton. This story invites us to dive into these first decades of study, to understand the methods used, the observations made, and the fundamental role that Neptune plays in nautical ephemerides, indispensable for long-distance navigation. Everything begins just 17 days after the confirmation of the discovery of the planet. To everyone's surprise, astronomers spot a bright point in the immediate vicinity of Neptune, a point unknown on celestial maps. Over the nights, they observe that it follows the planet closely, describes an orbit around it, and shines consistently. It is quickly understood that this is a satellite, soon named Triton. It is rare at that time to discover a planetary companion so soon after identifying the planet itself. This observation arouses keen interest because the presence of a massive satellite can provide valuable insights into Neptune's mass through the study of its orbital movements. Astronomers already know that the path of a satellite depends on the gravitational force exerted by the planet. By precisely timing its revolution and distance, they can estimate the attraction exerted by Neptune. Through these calculations, they obtain the first estimates of its mass. This approach is fundamental, as the means of studying distant stars remain very limited. Scientists notice that Triton follows a retrograde trajectory around Neptune. In other words, it orbits in the opposite direction to the planet's rotation on its axis. This unexpected behavior leads to the hypothesis that Triton was not born at the same time as Neptune, but was captured later by its gravity. The astronomers of the late 19th century do not yet have the techniques to confirm this scenario with certainty, but this hypothesis gains ground. Indeed, the analysis of its orbit shows behavior distinct from that of ordinary moons, which generally rotate in the same direction as the planet. Lacking the means, it is difficult to go further. Astronomical photography is in its infancy, and telescopes capable of probing these regions of the sky remain rare. Parallel to the discovery of Triton, another endeavor emerges, measuring the diameter of Neptune. Scientists are trying to refine the evaluation of its apparent size, that is, the angle under which it is seen from Earth. For this, they perfect telephotometry techniques. This method involves comparing the light received from Neptune to that of objects whose brightness is known. They also use instruments equipped with micrometers, which allow the measurement of very small distances in the telescope's field of view. These devices, by moving a fine reticule in the eyepiece, make it possible to measure the gap between two bright points with a precision that can reach a fraction of an arc-second. The arc-second is essential for understanding these measurements. A complete circle contains 360 degrees, each divided into 60 arc-minutes, themselves composed of 60 arc-seconds. A single degree, therefore, corresponds to 3,600 arc-seconds. When it is said that Neptune has an apparent diameter of about 2.4 arc-seconds, it means that it would take aligning 1,500 diameters of Neptune to cover a single degree of sky. It's extremely small, and this illustrates the difficulty of determining this planet's characteristics. Thanks to this method, astronomers estimate that the apparent diameter of Neptune is around 2.4 arc-seconds. By cross-referencing this data with the average distance between Neptune and Earth, they obtain an estimate of its actual diameter. They discover that, although it surpasses Earth in size, Neptune remains less impressive than Jupiter or Saturn, the dominant gas giants. They also strive to assess its density to better understand its composition. A high density suggests richness in heavy materials, while a low density indicates a predominance of gas or ice. By the end of the 19th century, researchers conclude that Neptune, much more massive than our planet, presents a lower density than Jupiter or Saturn. In the absence of space probes, they deduce that Neptune is probably composed mainly of ices and gases, without a rocky core as large as Earth's. These data, although partial to our modern eyes, represent an achievement. By relying on the laws of celestial mechanics, astronomers obtain a credible estimate of Neptune's mass. They meticulously observe the orbital period of Triton, note each passage at the same point in its orbit, and carefully record each measurement. Long calculations by hand support these observations. Without calculators or computers, everything rests on rigorous observation and meticulous verification of results. This work demands remarkable discipline, but it enables significant advances. The dynamics of Neptune become sufficiently well known to be integrated into the first nautical tables. The ephemerides used by navigators are tables indicating the predicted position of celestial bodies day by day. Until the mid-19th century, sailors primarily rely on the moon, the sun, or certain visible planets to determine their position. With the addition of Neptune in these documents, more checks can theoretically be performed when calculating geographical coordinates. Of course, Neptune, being very dim, remains unusable without optical instruments, and its use remains marginal. However, its integration into the ephemerides marks an important step in understanding the solar system. Each cataloged object enriches knowledge of celestial mechanics, and these data can, in some cases, be used to adjust universal time or to test new models of astronomical calculation. The end of the 19th century is also the time when photography transforms astronomical practice. Telescopes are equipped with sensitive plates, still not very efficient but promising. The first images of Neptune, although blurry by our current standards, become valuable archives. By combining visual measurement and photography, astronomers compare over time their estimates of the planet's diameter, the position of Triton, and other variables. They revise their calculations from one session to another, improving accuracy and reducing uncertainties. Interest in Neptune remains constant. It evolves alongside innovations in telescope lenses and mirrors. In Europe and the United States, several observatories launch regular observation campaigns. Astronomers exchange their data by mail, publish in specialized journals, and strive to harmonize their results. Interpretations differ, notably regarding Neptune's density. Some consider it similar to that of Saturn, others see it as a denser planet. These disagreements stimulate research and encourage rigor. Thanks to this scientific fervor, the period 1846 to 1900 lays the solid foundations for the study of Neptune. Estimates of its size are refined, its mass becomes more precise, and the singular trajectory of Triton gains legitimacy. These discoveries are accompanied by the update of astronomical tables, where Neptune now appears among the giants of the solar system. At the very beginning of the 20th century, astronomers embarked on an increasingly ambitious challenge, understanding the chemical composition of Neptune, this distant planet already shrouded in mystery. The instruments at observatories were still elementary compared to current standards, but advanced enough to lay the foundations of a method set to transform astronomy, spectroscopy. By decomposing the light emitted or absorbed by a star, This technique began to reveal essential clues about the gaseous nature of the blue giant. From 1900 to 1949, this period saw the refinement of these tools, but also the discovery of a satellite that would shake up the ideas about the movement of the body around Neptune, Nereid. A new stage was opening, featuring remarkable advancements and lively debates about this unexpected moon. At the turn of the century, the most advanced observatories methodically examined the light spectrum of Neptune. The principle of spectroscopy is based on the fact that when a material is exposed to light, it absorbs certain specific wavelengths. These absorption bands, visible through a spectroscope, allow the identification of elements or molecules. Like a cosmic barcode, each chemical substance leaves a unique signature in the form of dark lines in a colored spectrum. By directing their telescopes towards the outermost planet then known in the solar system, astronomers detected for the first time the significant presence of methane. Until then, this was merely a hypothesis based on comparisons with other giant planets. This detection therefore represented a major breakthrough. The demonstration of these absorption bands associated with methane provided a crucial clue about the nature of Neptune's atmosphere. Other troughs appeared in the collected spectra, suggesting the presence of lighter gases like hydrogen and helium, whose abundance varies depending on the planet. Gradually, astronomers introduced the notion of a frozen atmosphere, a term describing gases so cold they almost seem liquid. The farther one moves from the sun, the scarcer light and heat become. At billions of kilometers or miles away, Neptune is bathed in extreme cold, with temperatures dropping below minus 200 degrees Celsius or minus 328 degrees Fahrenheit. These figures were not yet precisely measured at the time, but the initial observations already pointed towards an extremely cold gas envelope. During this same period, spectroscopy experienced notable improvements: finer diffraction gratings, more reliable lenses, and more sensitive devices. Astronomers compared the light of Neptune to that of nearby stars to reduce the effects of Earth's atmosphere and isolate the methane signatures. Some even tried to estimate the concentration of this gas, despite the lack of sophisticated models to interpret the data. The measurements, although limited, gradually confirmed the major influence of methane, responsible both for Neptune's blue hue and the probable formation of clouds in its upper layers. These discoveries quickly piqued the interest of a public fascinated by astronomy. Newspapers relayed the research conducted by observatories like Mount Wilson or some European centers, which exchanged their photographic snapshots to refine their analyses. This growing cooperation marked a turning point in the dissemination of space sciences. The importance of studying all the giant planets to better understand the origin of the solar system was realized. Long overshadowed, Neptune regained a central place thanks to the increased precision of optical instruments and the growing enthusiasm of researchers. Over the decades, the continuous observation of Neptune was to bring a major surprise: the identification of a new moon. Until then, only Triton had been observed shortly after the discovery of the planet. But in 1949, astronomer Gerard Kuiper announced the discovery of a second satellite named Nereid in homage to the sea nymphs. The announcement provoked great enthusiasm both among scientists and in the general public. Highlighting a new celestial object orbiting Neptune, more than a century after its discovery, opened a new era of exploration of the outer reaches of the solar system. Nereid posed a real puzzle. Its orbit was among the most eccentric ever recorded for a natural satellite. An eccentric trajectory deviates significantly from the perfect circle. In Nereid's case, the distance to Neptune varies greatly over the course of its revolution. From the 1940s, scientists tried to understand this singularity. Why did this moon follow such an elongated trajectory, while Triton, on the other hand, maintained an almost circular orbit? A first hypothesis put forward was that of capture. An external object, when approaching Neptune, would have been caught by its gravity. For such an event to occur, a deceleration is necessary, caused by complex interactions or a collision. The object slows down, then becomes a satellite. Some researchers imagine that Nereid originated from a distant region like the Kuiper Belt, or that it was a former cometary nucleus. Once trapped, its orbit would have slowly evolved until reaching the observed profile. But this theory was not the only one. Other scientists believed that the moon Nereid might have formed in the vicinity of Neptune and then experienced a major disruption, such as a close encounter with an asteroid, altering its initially regular orbit. The means of the time, still limited, did not allow for a definitive conclusion. However, this discovery opened a vast debate on the mechanisms capable of sustainably associating a moon with a giant planet. In the absence of space missions, researchers relied on improved telescopic observations, repeated measurements in multiple centers, and the gradual accumulation of data to better understand Nereid's trajectory. In the wake of this, astronomers set out to determine the orbital period of this moon. They calculated that several months were necessary for Nereid to complete its orbit, at times moving significantly distant from Neptune. These calculations, complex without computer assistance, required comparing the moon's successive positions on photographic plates taken at regular intervals. Teams spread across different laboratories tracked a tiny luminous point, measuring its angular position relative to the reference stars. Everything was done manually, with extreme precision. Despite the challenges, the results confirmed a spectacular eccentricity, placing Nereid among the most puzzling objects in the Neptunian system. Parallel to this major discovery, the period from 1900 to 1949 was marked by a growing desire to understand the overall environment of Neptune. The signatures of methane, hydrogen, and helium suggested the existence of a complex energy reservoir, fueled by both the remaining sunlight and an incompletely understood internal heat. Researchers sensed that invisible forces, possibly related to gravitational compression, played a role in the atmospheric dynamics. They also suspected that these factors influenced the orbits of satellites like Nereid. As the 1940s progressed, data processing methods and the quality of optics continued to improve. The spectrums collected were compared across observatories. Interest also grew in the light reflected by the planet and its moons. Nereid's highly elongated orbit implied brightness variations depending on its distance from Neptune and the planet's position around the Sun. Hypotheses emerged. Perhaps the brightness variations revealed a partially icy surface or an irregular shape, but the instruments of the time were still not capable of providing definitive answers. By the late 1940s, Nereid established itself as a crucial object for better understanding Neptune's outer environment. The unique orbit of this moon reinforced the idea of a complex history. Meanwhile, spectroscopic analyses were advancing. Methane's role in absorbing visible and infrared light seemed confirmed, explaining Neptune's distinct blue hue. Scientists now hope to detect other gases like ammonia or water vapor, but technical limitations prevented any certainty. Nevertheless, spectroscopy continued to develop, benefiting from a better understanding of atmospheric disturbances thanks to nearby reference stars. The discovery of Nereid, officially recorded in 1949, marked the culmination of nearly half a century, characterized primarily by the recognition of Neptune's gaseous and icy nature. While discussions persisted about the exact proportions of its gases, a consensus was forming around an atmosphere dominated by methane, hydrogen, and helium. Neptune resembled other gas giants while distinguishing itself with its density, powerful winds, and now a richer system of moons than previously imagined. Testimonials from researchers of the time reveal a mix of fascination and frustration. They sensed the complexity of the Neptunian world while confronting the limitations of their instruments. Only the increasingly powerful telescopes enabled progress, driven by perfected mirrors, stable mounts, and refined photographic processes. Between 1900 and 1949, Neptune thus transitioned from the status of a distant celestial body to that of a planet with multiple faces. The detection of methane, made possible by increasingly advanced spectroscopy, revealed a world dominated by cold gases, responsible for its blue color. The discovery of Nereid, with its strange orbit, introduced a profound question. Did this moon come from elsewhere? This mystery laid the groundwork for a broader debate on how giant planets acquire new companions. In the decades to come, astronomers would patiently continue their quest, determined to unravel the secrets of Neptune's icy realm, its distant gases, and its enigmatic moons. Between the mid-20th century and the late 1970s, Neptune began to unveil its mysteries. This progress was made possible by the rise of radio astronomy and the rapid advances in high-resolution photography. The astronomers and engineers of that era were able to build on the legacy of the pioneers in the field, whose research directly followed the discoveries of Karl Jansky, made in the 1930s. From 1950 to 1977, increasingly powerful radio telescopes emerged, sometimes called Jansky-style, in homage to the man who first detected signals from the Milky Way. Over these decades, the scientific community finally obtained detailed data on Neptune's radio emissions. These signals revealed thermal emission, typical of a planet with a complex atmosphere and internal heat. To measure the significance of this advance, it must be remembered that until then, the planets of the solar system were primarily observed through classic optical telescopes. The images obtained were often blurry, with low contrast, particularly for Neptune, which is more than 4 billion kilometers, or over 2 billion miles away. The advent of radio astronomy changed the game. Astronomers stopped limiting themselves to visible light and began capturing radio waves, much longer, capable of revealing the heat emanating from the atmosphere and the interior of planets. For Neptune, these emissions came primarily from its atmospheric structure. The instruments of the time began to map this faint glow with unprecedented precision. Among the major discoveries from these observations was the confirmation of an extremely low temperature at a certain level of Neptune's atmosphere, about minus 218 degrees Celsius or minus 360 degrees Fahrenheit. This region is called the tropopause. In a planet's atmosphere, the troposphere is the lowest layer, where temperature decreases with altitude. At a certain boundary, the temperature stops dropping and may even rise. It is at this turning point that the name tropopause is given. On Neptune, this boundary separates most of the clouds from the stratosphere. Discovering that this area reached such an icy temperature allowed for a better understanding of the extreme cold of its atmosphere, far beyond that of other gas giants. Thanks to radio waves, researchers also began to suspect the presence of an internal heating mechanism, possibly linked to the dissipation of gravitational energy or the slow cooling of the planet since its formation. But the contributions of radio telescopes were not limited to temperature. They allowed for insights into gas dynamics and atmospheric movements. Radio waves, capable of penetrating layers opaque to visible light, opened a new window onto the planet's internal chemistry. Even though the sensitivity of the instruments remained limited, the data collected showed that Neptune was not a sphere frozen in darkness. Debates on the composition of its atmosphere intensified, suggesting the possible presence of methane, hydrogen, and helium, despite the uncertainty of the measurements, which required complementary analyses in other wavelengths. In parallel, high-resolution photography made great strides. With the improvement of photographic films and the enlargement of terrestrial telescopes, observatories equipped themselves with specialized cameras using rudimentary adaptive optics or atmospheric filtering techniques. This is how infrared images of Neptune were captured over long periods. Infrared, located between radio waves and visible light, allowed for the detection of temperature variations, revealing the presence of cloud bands arranged mostly parallel to the equator. For the general public, these infrared images sometimes seemed less impressive than photos in visible light, as they didn't show Neptune's famous bluish tint. But for researchers, they were crucial. They allowed for estimating the speed of the clouds and, thus, calculating the rotation duration of the planet. It was in the 70s that it was established that Neptune rotates on its axis in about 16 hours. This figure wasn't easy to determine, as the absence of a visible surface forced reliance on the movement of the clouds, which themselves were subject to powerful winds. It was known, thanks to Jupiter and Saturn, that the deep rotation could differ from that of the magnetic field. On Neptune, only atmospheric data allowed for an estimation. Despite the uncertainties, this measurement of a fast rotation marked an important step. It was already acknowledged that gas giants rotated quickly, between 10 and 17 hours, depending on their size and density. These new data confirmed that Neptune, although more distant, shared certain dynamic properties with its neighbors. Yet, it remained the most distant and least observed. Astronomers, whether working with radio telescopes or infrared cameras, had to contend with the enormous distance separating Neptune from Earth, making signal reception particularly difficult. In this empirical context, the first hypotheses regarding Neptune's internal structure and atmospheric dynamics emerged. The analysis of this heat sent back into space showed that the planet wasn't just a simple gaseous mass. It began to be considered that there could be internal movements, perhaps related to convection, where the heat from the core would rise to the upper layers. Signals captured by Jansky-style radio telescopes proved that at this distance, Neptune maintained active, energetic processes. Scientists were already questioning the origin of this flow, simple residue from formation, or a more complex phenomenon involving the gradual separation of elements at the planet's core. These discoveries also had an impact beyond the scientific community. The first media repercussions introduced the public to the power of radio astronomy and the richness of infrared images. These photographs, often reworked in false colors to enhance contrasts, showed cloud structures that couldn't be otherwise distinguished. This process, which assigns colors to infrared intensities, produced striking images. Thanks to this, several cloud belts could be identified, initiating a finer study of Neptunian meteorology. Through scientific publications that appeared between 1950 and 1977, Neptune took shape, a frigid planet with a tropopause at -218 degrees Celsius or -360 degrees Fahrenheit, and animated by a rapid rotation of about 16 hours. Without space probes to approach it, astronomers were learning to decipher the atmospheric activity of a distant world using two key instruments: radio telescopes sensitive to millimeter or centimeter waves, and infrared photography, whose definition was improving. Despite everything, precision remained limited, and many questions remained. The exact origin of certain structures was not yet understood, nor was the global dynamic of the atmosphere. Yet, this period was decisive. It prepared the ground for the space missions that would later explore the outer reaches of the solar system. Even if it goes beyond our immediate topic, it is clear that without emerging radio astronomy and nascent infrared photography, scientists would not have been able to refine their predictions for future observations. Thus, between 1950 and 1977, a new discipline asserted itself, planetary radio astronomy, and with it, a more precise vision of Neptune. An atmosphere of extreme cold, a boundary layer between the troposphere and the stratosphere, and cloud bands indicative of a complex internal dynamic. Being able to identify these cloud formations, even rudimentarily, laid the groundwork for the study of the planet's climate. Thanks to infrared data, researchers understood that some clouds, brighter ones, indicated active motions, likely related to the condensation of compounds like methane or hydrogen in convection zones. It was already suspected that these currents could form storms, although nothing was confirmed yet. The rapid rotation, estimated at 16 hours, pointed to intense dynamics, foreshadowing the later discovery of the most violent winds in the solar system. Between the late 70s and the late 80s, the Voyager 2 spacecraft, sent by NASA, embarks on a long journey through the solar system, eventually reaching distant Neptune. This event, occurring on August 25, 1989, marks the only time humanity has been able to closely observe this icy blue giant. This story takes us through this period, from 1977 to 1989, through a documentary-style narrative. The journey begins with the preparations for the Voyager mission, progresses step by step to the historic flyby of Neptune, and concludes with the major discoveries of the probe, the Great Dark Spot, supersonic winds, new moons, and the strange temperature of the upper atmosphere. In the mid-70s, NASA plans two almost identical probes, Voyager 1 and Voyager 2, designed to conduct a grand tour of the giant planets. It is in 1977 that Voyager 2, despite its name, is the first to launch, taking advantage of a rare planetary alignment. Its initial mission, to reach Jupiter, then Saturn, and if all goes well, to continue on to Uranus and Neptune. At the time, these worlds were still largely unknown, observed only from Earth or by orbiting telescopes. Scientists hoped to obtain close data, as only a probe could offer a direct view of these distant planets. After several years of travel, punctuated by successful flybys of Jupiter in 1979 and Saturn in 1981, Voyager 2 continues its journey to Uranus, which it reaches in 1986. This first visit to such a distant planet is already an accomplishment. Only after this stage does NASA confirm the possibility of extending the mission to Neptune, even farther away. The ground team then mobilizes to define the trajectory and necessary maneuvers. The years pass, preparations intensify, and excitement builds as the rendezvous approaches. The key moment occurs on August 25, 1989, a date that enters the annals of space exploration. As the probe approaches, the images become clearer. A vast dark spot is discernible against a deep blue background. Researchers nickname it the Great Dark Spot, by analogy with that of Jupiter. But here the phenomenon is unstable, appearing and disappearing at different locations on the planet, revealing a much more changeable nature. As Voyager 2 grazes Neptune a few thousand kilometers or miles from its upper atmosphere, it transmits astonishing data. Winds blowing at nearly 600 meters per second or 1,312 miles per hour. This is equivalent to over 2,160 kilometers per hour or 1,343 miles per hour, a supersonic speed in this icy atmosphere. Scientists are astounded. At such a distance from the sun, where light and heat are scarce, Neptune still maintains storms of extreme power. These furious winds swirl around the great dark spot, forming a weather system as fast as it is chaotic. Among other major revelations, confirmation of the presence of rings around Neptune. Their existence had been suspected, but remained to be demonstrated. Voyager 2 detects two main rings, named Adams and Leverrier, in honor of the astronomers who had predicted Neptune's existence. At first glance, these rings appear diffuse, far from the spectacle offered by those of Saturn. But upon closer inspection, irregularities in density, variations in light, arcs, and zones of accumulation are observed, indicating a much more complex structure than it seems. The probe also dedicates a part of its passage to the study of Neptune's satellites. Before this flyby, only a few moons were known, such as Triton, identified in the 19th century, and Nereid, discovered in the 40s. Voyager 2 identified 6 more, all internal: Despina, Larissa, Proteus, Galatea, Thalassa, and Naiad. Each has its own characteristics. Proteus, for instance, is larger than expected, with an irregular shape typical of icy moons. Larissa, long suspected, is finally confirmed. These discoveries enrich the understanding of Neptune's gravitational environment, revealing its influence on these small orbiting bodies. During the observation of the rings, subtle phenomena appear, density waves. Simply put, these are compression waves in the rings, comparable to the wakes left by a ship. These patterns, caused by moons or clusters of matter, illustrate the complex dynamics that reign between Neptune, its satellites, and the icy particles of its rings. Beyond the winds and the great dark spot, another point intrigues scientists: the temperature measured in the stratosphere. Despite the extreme distance from the sun, nearly 4.5 billion kilometers or 2.8 billion miles, this region of the atmosphere has a higher temperature than expected. It remains negative, of course, but this level of warmth suggests an internal source might exist, perhaps linked to gravitational dissipation, radioactive elements, or an energy mechanism fueled by violent winds. This mystery remains unsolved, but highlights the complexity of Neptune's climate. This flyby is not limited to a series of spectacular shots. It radically transforms the image we had of this planet. Before Voyager 2, Neptune seemed similar to Uranus, calm, dull, without prominent features. However, what the data reveal is a living world, traversed by clouds, storms, violent currents, and striking atmospheric phenomena. The period from 1977 to 1989 remains unique, as since then, no other probe has approached Neptune so closely. The brief passage of August 1989 captivated both scientists and the public. On board, Voyager 2 carried various instruments: cameras, spectrometers, particle detectors, and a magnetometer, which enabled a rich portrait of this planet, despite the little time available. After completing its observation, the probe continued its journey towards the outer solar system, taking with it a set of data that fuels research even today and inspires future explorations. Remembering this mission is a reminder that an isolated planet, drowned in darkness, can harbor unexpected phenomena. The swift winds, atmospheric structures, fragmented rings, mysterious moons. all signs of cosmic diversity on the scale of our solar system. Neptune is not a dormant planet. It houses powerful atmospheric forces capable of defying the little energy it receives from the sun. August 25, 1989, thus marks the culmination of the Voyager 2 mission. On that day, the probe reveals the Great Dark Spot, swept by winds of 600 meters or 2,000 feet per second. It unveils rings animated by gravitational waves, as well as 6 new moons, each unique. And above all, it highlights a thermal mystery, proving that Neptune still holds many secrets. The period from 1977 to 1989, with the highlight of the encounter with Neptune, proved extraordinarily fruitful for science. This close passage offered a fascinating glimpse of a restless planet, surrounded by discrete rings and intriguing satellites. Since then, Neptune has returned to being a distant target, accessible only through land-based or orbital telescopes. But the traces left by Voyager 2 continue to influence research, as if Neptune whispered to us that it has not revealed all its secrets, and patiently awaits another mission to one day take up the torch again. Between 1990 and 2002, Neptune suddenly became one of the most prized observation grounds among astronomers worldwide. Thanks to the Hubble Space Telescope, launched in the same year of 1990, it became possible to track the evolution of a complex meteorology, marked by dark spots, isolated clouds, and strange luminous phenomena in the planet's upper atmosphere. Observing the most distant of the giant planets with such precision represented a major advancement at the time. The images transmitted from Earth's orbit, free from the turbulence of our own atmosphere, revealed a blue world swept by violent winds, with an internal dynamic that remained largely enigmatic. One of the noteworthy events at the beginning of this period was the sudden disappearance of the Great Dark Spot, which had been considered a visual signature of Neptune since Voyager 2 flew by in 1989. During this historic passage in the late 1980s, the Voyager 2 probe had revealed a massive storm similar to a Neptunian version of Jupiter's famous Great Red Spot. This atmospheric structure, known as the Great Dark Spot, covered an area equivalent to that of Earth. Oval in shape, it stood out distinctly against the planet's deep blue. The first images received after the Voyager's passage led to the belief that this storm would remain visible for a long time, similar to Jupiter's persistent vortices. However, when Hubble pointed its mirror at Neptune in the early 1990s, astronomers were astonished to discover that the spot had completely disappeared. This surprise revealed how rapidly Neptune's atmosphere could evolve. Researchers understood that despite its extreme distance, this icy giant, located more than 4 billion kilometers or 2.5 billion miles from the sun, experienced rapid weather changes. No one expected to see such a vast structure vanish in such a short time. Among the hypotheses proposed to explain this phenomenon were disturbances in atmospheric currents or in the distribution of heat within the planet. With winds reaching more than 2,000 kilometers per hour or 1,043 miles per hour, Neptune clearly defied classical climate models. Shortly after this disappearance, a new dark spot appeared in the northern hemisphere. Hubble, whose image quality was improved by a maintenance mission, allowed astronomers to observe this new vortex with unprecedented precision for that era. This second structure, often seen as the sister of the first, confirmed that Neptune's storms were not fixed. They formed, moved, disappeared, revealing a world in perpetual transformation. This was a crucial clue. The dark spots were born from the meeting of strong opposing winds, creating low-pressure areas where cold air formed these impressive vortices. To understand their striking visual appearance, one must look at the composition of Neptune's atmosphere, dominated by hydrogen, helium, and a significant amount of methane. This atmosphere absorbs a large portion of red light, giving the planet its characteristic blue color. When a storm raises deeper layers, color contrasts become visible. These formations appear clearly in the visible light spectrum, but even more so in wavelengths like ultraviolet or infrared. It was this richness of observation offered by Hubble that allowed for unveiling part of the planet's meteorological mysteries. At the same time, another scientific advancement emerged: ultraviolet observation, thanks to a method called ultraviolet photometry. This allows the measurement of light emitted by a celestial object within a specific band of the spectrum. By focusing on the ultraviolet, researchers hope to detect energetic phenomena, notably the excitation or ionization of molecules in the upper layers of the atmosphere. On Earth, this technique allows the study of polar auroras, which appear when particles interact with the magnetic field, emitting a characteristic light in the sky. On Neptune, it was during this same period that the presence of auroras was suspected for the first time, much fainter than those on our planet or Jupiter. These phenomena occur when particles from the solar wind reach the magnetic poles and collide with atmospheric gases, causing light emission. On Earth, they form colorful ribbons in the sky. On Neptune, their glow would be barely perceptible, even up close. However, the sensitivity of Hubble's sensors, enhanced by sophisticated digital processing, highlighted possible luminescent areas at the poles. One of the major challenges in confirming these auroras lies in Neptune's unique magnetic geometry, tilted and offset from the planet's axis. Thus, solar particles do not penetrate it evenly. Astronomers then attempted to map the ultraviolet light variations in the polar regions. The data collected in the late 1990s and early 2000s seemed compatible with the existence of these glows. However, proving their direct link to magnetic activity remained. The teams continued their observations in the hope of obtaining irrefutable evidence. Research conducted during this decade also allowed for a better understanding of how Neptune reacts to the weak sunlight it receives. So distant, the planet captures only a faint glow compared to Earth. Yet, its clouds and storms, fueled by upwellings of liquid methane or hydrocarbon ices, remain surprisingly dynamic. Contrary to popular belief, the sun is not the primary driver of this activity. The planet's internal heat plays a crucial role. Measurements made by Hubble showed that Neptune emits more energy than it receives, which would explain the vigor of its weather systems, their rapid winds, their vortices, and their unpredictable evolution. At the end of this period of more than 10 years, astronomers painted a first detailed portrait of Neptune's climate variability. The rapid disappearance of the Great Dark Spot defied all expectations. The appearance of a new spot in the opposite hemisphere suggested the existence of a recurring mechanism. Finally, ultraviolet observations reinforced the hypothesis of discrete but real auroras. These phenomena, although faint, challenged our understanding of the planet's magnetic field, which is evidently unstable or complex. Thus, between 1990 and 2002, Neptune unveiled an active weather system and a much more dynamic atmosphere than previous observations had suggested. Thanks to Hubble, the study of Neptune turned out to be much more enriching than a mere exercise in remote photography. Structures capable of appearing and disappearing within a few years were discovered, vortices capable of migrating from one hemisphere to another, and nearly invisible, but nonetheless present, polar glows. This decade laid the foundations for a more in-depth exploration of the planet and its climate, paving the way for future, more advanced instruments. It also showed how valuable it was to track the evolution of dark spots and bright clouds over time, as each of these changes told part of the complex atmospheric puzzle of this distant world. Between 2002 and 2013, a pivotal period opened in the exploration of Neptune. Small moons and previously unsuspected rings gradually revealed themselves to astronomers. Thanks to the giant Subaru and Keck telescopes, located on the heights of Mauna Kea in Hawaii, researchers followed a series of previously invisible clues. These seemingly subtle discoveries, however, unveiled fundamental elements of the dynamics of the Neptunian system. Let's observe step by step how the quest for irregular satellites, combined with the study of faint rings, transformed our understanding of this distant planet and its cohort of celestial bodies perched on the fringes of the solar system. In the early months of 2002, several teams began scrutinizing the area around Neptune, hoping to detect unknown objects. This research is driven by the peculiarity of many orbits around the planet. Satellites like Triton already follow atypical trajectories, while other smaller moons seem to move in an unstable manner, possibly indicating gravitational captures or past collisions. These are termed irregular because they do not follow a circular orbit oriented in the usual direction. Their inclined or retrograde paths suggest a distant origin, perhaps anchored in the icy region of the Kuiper Belt. This field of study mixes numerical analyses, high-precision observations, and bold hypotheses about the formation of planetary systems. In this context, an announcement is made: the detection of S2002N1. Its identification proves complex, with Neptune over 4 billion kilometers, or about 2.5 billion miles from the Sun, making small objects difficult to spot. However, the Subaru and Keck telescopes, sensitive to visible and near-infrared light, discern a slowly moving point in the images around the planet. Its trajectory, far from circular, significantly differs from that of regular moons. Astronomers then suspect an additional body, probably an irregular satellite captured or resulting from a collision. Its orbit, measured over several months, shows marked eccentricity, confirming its unique character in the Neptunian environment. Subsequently, two other moons are identified, Halimede and Psamathe, inferred from the same series of images. Halimede intrigues with its highly inclined orbit, while Psamathe follows a distant trajectory, almost at the edge of Neptune's gravitational domain. Their detection relies on observing the subtle movement of a luminous point from one image to another. The telescopes, set over 4,000 meters or about 13,123 feet high, use adaptive optics capable of compensating for atmospheric turbulence. The result: clearer images that facilitate the detection of these faint and slow objects. As data accumulates, researchers undertake long calculation sessions to estimate the mass and radius of each satellite. The results remain approximate, as the perceived light is only a thin reflection. Halimede appears to measure a few dozen kilometers or miles, while Psamathe is likely even smaller. The exact size remains uncertain. It all depends on reflectivity, which, if lower than expected, would make the object larger than it appears. Despite these uncertainties, scientific dialogue progresses. Hypotheses abound: fragments from collisions, objects captured by Neptune during its primitive evolution. Astronomers explore all avenues in light of what is known about the moons of giant planets. During this decade, research extends beyond satellites. Neptune's rings, glimpsed by Voyager 2 in 1989, are rigorously observed from Earth. Unlike Saturn's, they are composed of dust and dark debris, distributed in discontinuous arcs. High-resolution instruments examine the influence of internal moons on the structure of these rings. Sometimes, gravitational interactions cause density waves that condense matter in places, giving rise to ephemeral formations. Their low brightness does not diminish their importance. They contain crucial clues about past collisions or recent migrations of objects. Over the years, suspicions grow about the presence of other still invisible tiny moons. The structure of the dust disk suggests that many small bodies orbit the planet. Astronomers scrutinize every image, awaiting a faint glimmer. This quest relies on algorithms capable of discerning the weakest signals, often drowned in cosmic noise. Subaru, Keck, but also Gemini and space telescopes take turns regularly covering Neptune's vicinity. In 2013, these efforts bore fruit. Researchers announced the discovery of a new object, named Hippocamp, after several verifications. Named after a mythological sea creature, it stands out due to its small size, approximately 34 kilometers, 21 miles, in diameter. Upon the announcement, a hypothesis emerged. Hippocamp might be a fragment of another more massive moon. Analyses directed attention toward Proteus, discovered by Voyager 2. An ancient impact could have expelled a large enough block to form an independent satellite. Trajectory and energy calculations make this scenario credible, although further studies are needed. Why target Proteus? First, because Hippocamp orbits nearby. Next, because its appearance resembles debris, rather than an object formed from the initial collapse of matter. Finally, Proteus features a gigantic crater named Pharos, a visible trace of a violent impact. According to scientists, this impact could have projected fragments, one of which escaped destruction to become a moon in its own right. This hypothesis, difficult to prove formally, is based on consistent observations. The study of Hippocamp also shows how icy bodies around Neptune can evolve unexpectedly. A simple impact hundreds of millions of years ago can still leave a stable imprint today. This revelation complicates the vision of the Neptune system. Beyond imposing moons like Triton or irregular masses like Proteus lies a multitude of fragments telling a more fragmented, dynamic story. It appears that Neptune's influence is not limited to a few dominant moons, but extends to an entire swarm of satellites, sometimes barely perceptible. Studies dedicated to Hippocamp, S2002N1, Halimede, and Samathe, reinforce the idea that Neptune forms a true celestial laboratory. Researchers explore the consequences of collisions, the effects of gravitational capture, and the diffuse debris in the rings. Time is an acting force there. Slow erosion, orbital rearrangements, material migrations over immense periods. Observing these processes is akin to contemplating a system in perpetual metamorphosis. Thus, the decade 2002 to 2013 witnessed the identification of several irregular satellites and the discovery of Hippocamp, a micromoon 34 kilometers, 21 miles, in size, perhaps born from an ancient collision with Proteus. These advancements, made possible by exceptional Earth-based telescopes, have transformed our view of Neptune. Exploring this remote region is a dive into a universe where every grain of rock or ice bears the scars of a cosmic history. Neptune, famous for its titanic storms, also asserts itself as a discreet haven for these wandering companions, formed in violence or captured in silence. This phase of observation, crucial for studying irregular moons, embodies a new dynamic, relentlessly probing the confines of Neptune to unveil its diversity, movement, and hidden grace. For even billions of kilometers from the Sun, other worlds still await discovery, bearing essential clues about the origin and evolution of the solar system. From its orbits, Neptune continues to surprise scientists since its discovery in the 19th century. Between the occasional visits by probes and constant surveillance by large telescopes, the blue planet reveals fascinating atmospheric phenomena. Between 2014 and 2021, attention focused on the rapid evolution of giant storms and the appearance of mysterious dark spots in its icy atmosphere. The Hubble Space Telescope proved decisive, notably capturing the unexpected trajectory of a dark vortex in 2020. These years offered a series of unprecedented observations, shedding light on the complex dynamics of Neptune's winds and currents. At these extreme latitudes, equatorial winds can reach hundreds of kilometers per hour. These flows, similar to rivers of air, influence the formation of methane clouds. This gas, present in the atmosphere, condenses at very low temperatures, giving rise to bright, moving, and changing cloud layers driven by whirlwinds. Hubble has detected several dark spots, identified as vortices or anticyclonic storms. Unlike earthly storms, these structures do not produce rain, but lift thick clouds of methane. One of the noteworthy discoveries involves a vortex, which, after approaching the equator, suddenly moved back towards higher latitudes. This turnaround has intrigued researchers who are trying to understand the mechanisms behind this phenomenon. Until then, it was believed that these spots disappeared upon reaching the equator, a particularly unstable zone on Neptune. But in 2020, a vortex defied predictions by reversing its trajectory. The joint study from several observatories has allowed a new hypothesis to emerge, linking the internal stability of the vortex to its interaction with transverse winds. This cooperation has proven the value of combining instruments to decipher the workings of Neptune's atmosphere. To monitor these storms, researchers use high-resolution imaging, spectroscopy, and photometry. Imaging provides information on the shape and position of the vortices. Spectroscopy reveals their chemical composition, notably methane in various states, and photometry records light intensity, unveiling the thickness and altitude of the clouds. By combining these tools, it has been possible to track almost daily the evolution of the dark vortex and better understand how the currents provide it with energy and cohesion. Methane also plays a key role in Neptune's blue color by absorbing the sun's red light. When it condenses in the coldest regions, it forms thin clouds that dissipate and reform quickly. At these altitudes, the temperature drops to around -200 degrees Celsius or -328 degrees Fahrenheit, allowing the methane to partially solidify. A minimal variation in winds can then trigger new cloud formations, showcasing the extreme reactivity of this atmosphere. During this period, numerous ground-based observatories contributed to the monitoring of Neptune, among them the Very Large Telescope in Chile and several radio telescopes. This global surveillance has highlighted the complexity of what some call the flying climate of the planet, where storms appear and disappear within a few years. The dark spots, signs of powerful vortices, emerge and then rapidly fade. This instability makes Neptune a natural laboratory for testing our climate models under extreme conditions. These dark spots, colder and darker than their surroundings, sharply contrast with the bright clouds composed of methane ice. In 2020, one of these vortices abruptly changed course, sparking the curiosity of the scientific community. Some suggest it may have encountered another cloud system, causing an alteration in its altitude and a lateral shift. This scene illustrates the sensitivity of Neptune's vortices to their environment, shaped by rapid winds and marked thermal contrasts. Measurements have shown that equatorial winds are even faster than expected, sometimes reaching over 1,000 kilometers or 621 miles per hour. This intense flow favors the mixing of air and the formation of methane clouds. When these currents intensify, they transport methane to the upper layers, where it condenses into clouds. Conversely, when activity weakens, the clouds dissipate, revealing the planet's typical blue hue. This perpetual cycle reflects an atmosphere in constant transformation. A central question remains: how long can these vortices last? On Jupiter, the Great Red Spot has persisted for centuries, but on Neptune, comparable structures disappear within a few years. The data collected show that the balance between the vortex's strength and the surrounding winds is much more delicate. To explain the altered trajectory of the observed vortex, some suggest a sporadic influx of energy, possibly linked to methane. The lifespan of these whirlwinds remains largely mysterious. Closer monitoring has revealed that Neptune's climate varies from year to year. Although the planet takes 165 years to complete its orbit around the Sun, its atmosphere undergoes much faster upheavals, hence the expression flying climate, which describes the extreme variability of its weather systems. Discoveries made between 2014 and 2021 show just how surprising this distant world can be. Each season brings its own set of events, and understanding them requires regular observations since this planet changes faster than once believed. Ultimately, the period from 2014 to 2021 illustrates the abundance of Neptune's atmosphere. The storms, dark vortices, and methane clouds follow one another, gradually unveiling the secrets of the wind circulation and thermal balance. Hubble played a crucial role, notably in detecting the vortex that changed direction. Cooperation between different observatories has provided a fuller picture, highlighting the importance of exploiting the entire light spectrum to unravel the mysteries of such an environment. These dark spots, true markers of meteorological activity, show how the climate of the blue giant defies predictions. Analyzing these phenomena offers a rare glimpse into the dynamics of planetary atmospheres under extreme cold and pressure conditions, and reminds us of the fascinating diversity of our solar system. These discoveries suggest that Neptune has not finished surprising us. In 2022, the James Webb Space Telescope offered astronomers an unprecedented view of the planet Neptune. In a dark sky populated with icy bodies, this blue giant was unveiled in a new light, thanks to exceptionally detailed observations. On July 12th, the telescope's near-infrared camera, NIRCam, captured images revealing 13 distinct rings, perfectly visible around Neptune. These circular structures, sometimes so thin, had never been observed with such clarity. Scientists were struck by the sharpness of these rings, as well as by the presence of bright ice clouds at very high altitudes. This observation marks a turning point in the study of icy worlds, shedding new light on the extreme conditions reigning at the edge of the solar system. To measure the scope of this advancement, one must first consider the difficulties involved in observing Neptune from Earth or its orbit. Located about 4.5 billion kilometers or 2.8 billion miles from the Sun, far beyond Saturn, Neptune appears dimly lit in telescopes. Its rings, made of dust and ice particles, are barely distinguishable. But thanks to the optical and infrared performance of the James Webb Telescope, positioned at a good distance from Earth, astronomers could capture revealing wavelengths. It is these light beams that brought to light the 13 rings, some of which were previously imperceptible. What is striking in these images are the bright, thin, and sparkling arcs that encircle the planet. Astronomers knew Neptune had a complex ring system, but this new observation revealed stunning details. The rings appear as icy ribbons, elongated and curved around the blue giant. Beyond their beauty, they offer clues about Neptune's internal activity and dynamic history, influenced by nearby moons or mechanisms still poorly understood at the planet's core. Alongside the rings, ice clouds have been detected in the upper layers of the atmosphere. Extremely bright in infrared, they form at altitudes where temperatures drop well below -200 degrees Celsius or -328 degrees Fahrenheit. Neptune is one of the coldest planets in the solar system, with an average of -218 degrees Celsius or -364 degrees Fahrenheit at the tops of its clouds. At such temperatures, water vapor becomes marginal, giving way to other ices responsible for these brilliant clouds. Researchers attribute their formation to the richness in methane and rare gases present in the atmosphere, which interact with infrared light to produce this luminous effect. Spectral analysis of the data has delivered another revelation. By examining the infrared light emitted or reflected by the planet and its rings, scientists detected gases like acetylene and ethane. On Earth, these compounds are involved in industrial processes. On Neptune, they indicate an active atmospheric chemistry. They result from the transformation of methane under the influence of ultraviolet radiation from the sun. Even at this extreme distance, these rays manage to trigger reactions in the uppermost layers of the atmosphere. This process has a name: ultraviolet photolysis. It involves the breaking of chemical bonds by sunlight. Methane, composed of one carbon atom and 4 hydrogen atoms, is the basic molecule. When fragmented by the rays, its elements recombine to form more complex compounds like acetylene and ethane. These reactions largely explain the diversity of gases detected on Neptune. They also influence its appearance as the particles produced sometimes descend into the atmosphere and modify its bluish hue. The presence of acetylene and ethane shows that even an atmosphere as distant from the sun remains sensitive to its influence. The distribution of these molecules on the planet could reveal atmospheric currents or thermal variations according to latitude or altitude. The new spectral data will allow for a more precise mapping of this complex chemistry and the potential existence of other compounds resulting from the same reactions. The detection of the 13 rings by James Webb is not just a visual feat. It's a key to better understanding their origin and stability. More discrete than those of Saturn, Neptune's rings now appear more extensive than expected, populated with dust and icy particles. These elements would be continuously renewed, either by the disintegration of icy bodies in orbit or by impacts on the surfaces of the moons. With these images, researchers hope to quantify the brightness and density of the segments to deduce their dynamics. The ice clouds also raise many questions. They appear as bright spots or light bands floating at high altitude. Their formation results from the condensation of compounds under extremely low pressure and temperature conditions. Some scientists believe they are primarily composed of methane ice, while others mention more complex hydrates. Future studies, based on imaging and spectroscopy, should provide more insight into their exact composition. Neptune, nicknamed the Ice Giant, also stands out for its particularly dynamic weather. Images reveal transient cloud formations, which appear and then fade quickly. This instability reflects strong internal activity, driven by powerful winds, temperature variations, and constant interaction with solar energy. The variations detected in July 2022 suggest that these phenomena could be seasonal or the result of atmospheric oscillations that are still poorly understood. For the first time, the James Webb Telescope allows these processes to be monitored over time, with images and spectra of unprecedented quality. The identification of acetylene and ethane helps decipher the chemical reaction chains at work. Even under very reduced solar radiation, Neptune's atmosphere remains the scene of continuous molecular activity. Understanding these mechanisms will help us better grasp the evolution of planetary atmospheres and illuminate the dynamics of other similar worlds. What fascinates is that this active chemistry is triggered despite sunlight being 30 times weaker than on Earth. This simple illumination is enough to break the chemical bonds of methane, initiating a series of reactions that produce heavier molecules. This sensitivity indicates a receptive atmosphere, capable of reacting even in a cold and distant environment. The discovery of these compounds enriches our understanding of a system much more complex than it seems. The images provided by NIRCam also reveal irregularities in the distribution of grains or dust. Some barely sketched gravitational resonances suggest incomplete arcs around the planet. These structures would result from interactions between Neptune, its moons, and the particles in the rings. Some suggest that these rings are constantly evolving, eroding, or regenerating over time. The 2022 observations mark a decisive step in setting a reference point to which future images can be compared. For researchers, the discovery of 13 distinct rings is a valuable lever. It allows for detailed analysis of gravitational interactions, tracking the movement of matter around the planet, and better understanding the role of solar wind in the evolution of these structures. Simultaneously, chemical analysis paves the way for detecting other essential molecules. This research will help determine if similar phenomena exist on other planets, particularly among distant exoplanets. The images unveiled since the summer of 2022 have changed our perception of Neptune. For the first time, a discrete ring system appears with remarkable clarity, rivaling the interest of those of other giants in the solar system. The shimmering ice clouds add a spectacular dimension, while also raising unresolved questions about atmospheric dynamics. The fact that molecules used on Earth in the industry are found billions of kilometers or miles away reinforces the sense of unity in chemical laws across the universe. The data from the James Webb Telescope will continue to fuel research on the rings and photolysis for a long time to come. This 9th chapter in Neptune research illustrates how the most advanced space technologies transform our understanding of the universe. What was once just a blurry spot has become a precise infrared image, revealing 13 rings, high-altitude clouds, and distinct chemical signatures. This discovery opens new perspectives on atmospheric chemistry and the dynamics of the rings. In an isolated corner of the solar system, significant reactions continue, fueled by barely perceptible sunlight, while formations of ice swirl above the poles. A stunning demonstration that many mysteries remain to be solved on Neptune, and that the James Webb Telescope has only begun exploring this fascinating blue laboratory. Between 2003 and 2022, Neptune offered one of the most surprising observations in its history. During these 17 years, infrared instruments revealed an unexpected evolution in the overall temperature of this icy giant. A marked drop of about 8 degrees Celsius, 14 degrees Fahrenheit, was observed, followed by a sudden and localized warming at the South Pole. This complex change has raised many questions about the planet's internal workings and the physical mechanisms behind these variations. To fully understand this phenomenon, one must first know how the measurements are made. Astronomers use telescopes capable of capturing the thermal radiation emitted by a planet in the infrared. On Neptune, the light that reaches us is so faint that it must be carefully analyzed to determine the temperature of the upper atmospheric layers, where the most intense chemical reactions and meteorological phenomena occur. The changes observed between 2003 and 2022 therefore reflect a large-scale transformation. Scientific records, notably those from NASA programs in the Spitzer Observatory, show a clear trend. In the early 2000s, Neptune's stratosphere began to cool gradually, losing nearly 8 degrees Celsius, 14 degrees Fahrenheit. Such a decline on a planet as distant and slow to evolve as Neptune surprised the specialists. Despite its 165-year orbit around the Sun, Neptune demonstrates an astonishingly reactive atmospheric dynamic, highlighting the importance of continuing the observations. The stratosphere, the region above the tropopause, is a key area. It is where the temperature stops decreasing with altitude or even begins to increase. On Neptune, this layer is the site of complex photochemical reactions involving hydrocarbons. These substances are created from the interaction between sunlight, hydrogen, and methane, and could influence the thermal balance. Some scientists think that an imbalance in the production or destruction of these compounds might be responsible for the observed cooling. But the situation took an even more astonishing turn when a sudden warming appeared at the South Pole. While the overall temperature continued to drop, this region experienced an increase of several degrees. This stark contrast suggests the presence of distinct mechanisms acting simultaneously. Researchers then explored several avenues: the influence of the seasons, the distribution of solar energy, or even chemical reactions deep within the atmosphere. With an axial tilt close to 30 degrees, Neptune experiences true seasons, but their duration is exceptional. A single one can last several Earth decades due to the planet's very extended orbit. The most favored hypothesis to explain the temperature variations relies on this elongated seasonal cycle. Over the years, solar illumination changes slightly, modifying the photolysis of methane and other compounds present in the stratosphere. To better track this evolution, astronomers have relied on infrared data collected by several observatories. The Spitzer telescope, known for its great sensitivity, along with other ground-based instruments, have made it possible to monitor large-scale temperature variations. These combined efforts first highlighted the global drop, then the appearance of a polar microclimate where the temperature rose, marking a break with the general trend. Another potential explanation lies in the behavior of stratospheric hydrocarbons themselves. These compounds, sensitive to solar radiation and energetic particles from the solar wind, can absorb or release heat as they form or decompose. On the scale of Neptune, where sunlight is very attenuated, a simple shift in this chemical equilibrium could produce noticeable effects over time. This reality questions our perception of climate in the most remote regions of the solar system. Even at such a distance, Neptune exhibits significant thermal fluctuations on relatively short timescales. Some models even predict that this temperature decline could recur, linked to the renewal of aerosols in the upper layers of the atmosphere or disturbances affecting global circulation between the poles and the equator. The most recent analyses reinforce the idea of a deep seasonal cycle. Neptune's extremely slow revolution imparts each season with a lasting imprint. The presence of methane in the troposphere, combined with the effects of light at high altitudes, favors the formation of compounds, like ethane, capable of interacting with the residual heat of the planet. This energy, inherited from its formation and internal compression, escapes slowly into space. However, many uncertainties remain, particularly regarding the speed of the change. A variation of 8 degrees Celsius, 46 degrees, in less than 20 years is difficult to explain for such a massive and distant body. This enigma drives researchers to extend their observation campaigns, relying on increasingly advanced instruments. The James Webb Telescope, for example, will provide unprecedented precision on the chemical composition of Neptune's atmosphere and determine if these phenomena are cyclical or isolated. We are in the year 2023. Neptune, the most distant of the gas giants, unveils a new celestial spectacle. After years of observing the turbulence of its atmosphere, astronomers detect a new dark spot on its visible surface. This vortex, vast and swirling, indicates a large-scale atmospheric phenomenon. On August 24th, for the first time, an international team manages to capture a clear image of this structure from Earth, thanks to one of the most advanced observational instruments ever used. A remarkable feat, as detailing such a distant planet requires a level of analysis rarely achieved. This breakthrough was made possible thanks to the Very Large Telescope, installed in Chile's Atacama Desert. This observatory benefits from an exceptionally clear sky, ideal for astronomical exploration. Despite the distance that separates Neptune from our planet, optical technologies manage to cross this cosmic abyss and reveal unsuspected details. To achieve such clarity, researchers rely on adaptive optics systems, capable of instantly correcting the distortions caused by our own atmosphere. This is how they were able to distinguish this dark vortex, clearer and more contrasted than anything that had been observed so far. This type of vortex corresponds to a gigantic atmospheric circulation system evolving in Neptune's upper layers. At first glance, it resembles a cyclone, but its internal structure radically differs from what we know. On Neptune, winds reach vertiginous speeds exceeding several hundred meters per second, 1,000 feet per second. At these altitudes, methane clouds form in extreme cold, close to minus 210 degrees Celsius, or minus 344 degrees Fahrenheit. Scientists believe these dark spots are born in areas of high pressure, surrounded by rings of bright clouds. This configuration causes intense vertical movements, stirring gases and particles in the upper atmosphere. Upon detection of this anomaly, researchers precisely scrutinized its shape, size, and exact position on the planet's disk. For this, they used hypersensitive cameras capable of capturing different wavelengths. Each spectral band allows access to a specific layer of the atmosphere, as gases react differently to light. This method has made it possible to determine the vortex's altitude, as well as the speed of its internal flows. Initial analyses indicate that this disturbance covers several thousand kilometers or miles, making it one of the most imposing phenomena recently recorded on Neptune. This finding takes on even more meaning within the larger framework of planetary atmospheric dynamics. Since the Voyager mission in 1989, astronomers had already observed similar formations, but their lifespan seemed limited. Some disappeared after a few months. Today, thanks to increasingly powerful instruments, it becomes possible to follow these structures over the long term. The extreme sensitivity of the Very Large Telescope, combined with advances in image processing, now makes it possible to document the evolution of these vortices, their birth, expansion, or disintegration. After this first historic image, attention turned toward the future. A new observation campaign has been planned for March 2024, with the intervention of the Hubble Space Telescope. From its orbit, it offers unparalleled precision to examine Neptune. The data collected will complement those obtained from Earth. One of the priority objectives will be to track the vortex's trajectory and see if it develops further. According to initial findings, this structure could exceed 4,000 kilometers or 2,500 miles in diameter. On this scale, that represents nearly a third of the Earth's diameter, an enormity hard to conceive. Hubble's mission is crucial. Its position outside the Earth's atmosphere allows it to capture wavelengths inaccessible to ground-based telescopes. Its images, free from distortions, will offer an unmatched level of detail. Scientists thus hope to observe the air movements around the vortex, detect the formation of peripheral clouds, and estimate the depth of this system in Neptune's atmosphere. By cross-referencing this data with that from the VLT and other ground observatories, they will be able to detect rapid evolutions and map out a more complete picture of the planet's climate. Specialist projections also mention a possible link with Neptune's seasonal cycle. Although far from the Sun, the planet undergoes variations in sunlight, tied to a revolution that lasts 165 Earth years. When certain areas receive more light, even slightly, it can change temperatures in the upper atmosphere, promoting the formation of vortices. Researchers will therefore seek to determine if the phenomenon observed in 2023 coincides with the onset of a seasonal change. Such a coincidence would provide better insights into the internal mechanisms of the blue giant. The confirmation came in March 2024. Hubble has indeed detected a massive vortex located in the northern hemisphere, reaching a diameter of 4,000 kilometers or 2,485 miles. The images show a perfectly circular dark spot, encircled by a luminous halo where clouds appear at regular intervals. This system imposes a spiral motion on the surrounding winds, providing a stunning spectacle. Thanks to the resolution of the Space Telescope, the slightest variations in brightness are now detectable, as well as the gradual appearance of cloud formations at the periphery. This unique observation could provide decisive clues about how Neptune reacts to the weak solar energy inputs and the internal forces driving its atmosphere. We are at the beginning of 2025, and enthusiasm is growing within the astronomical community. For the very first time, the James Webb Space Telescope will observe in detail the polar regions of Neptune, in hopes of confirming a phenomenon never before detected at such a distance from the Sun. Launched several years earlier, the telescope operates in a gravitationally stable area known as Lagrange Point 2, 1.5 million kilometers, or 932,757 miles from Earth. Thanks to its exceptionally sensitive infrared sensors, it has established itself as a major tool for exploring the distant planets of the solar system. Until now, scientists suspected that Neptune, an ice giant discovered in the 19th century, harbored auroras comparable to those of Jupiter or Saturn. Previous studies had provided some hints that its magnetic field, as strange as it is powerful, could favor such manifestations. But the lack of direct observation left room for doubt. In April 2025, the James Webb, equipped with its NIR-SPEC infrared spectrograph, is set to focus its gaze on Neptune's poles for several hours, aiming to track down elusive lights. Polar auroras, known on Earth as northern lights in the northern hemisphere, are luminous phenomena caused by the interaction between the solar wind and a planet's upper atmosphere. Composed of protons and electrons stripped from the sun, this energetic flow travels at high speed through space. When it reaches a planet with a magnetic field, it redirects the particles toward the poles, where they encounter atmospheric gases, generating colorful lights sometimes visible from the surface. On Neptune, the challenge is immense to detect these signatures across a staggering distance. Finding a polar emission in the infrared is an outstanding achievement, as it testifies to the optical and electronic precision achieved by the telescope. In April, during a long-planned observation campaign, the James Webb spectrograph finally captures the hoped-for signals. Bright lights emerge from Neptune's poles. The data reveals that these are infrared emissions produced by trihydrogen ions, a structure formed by 3 hydrogen atoms bonded together, carrying a positive charge. Also called H3+, this particle is a recognized marker of auroral activity, as it forms when energetic particles strike the atmosphere, stripping electrons from hydrogen and causing infrared radiation. On such a distant planet, detecting these signals demonstrates that the solar wind, though weakened, still manages to trigger luminous reactions by interacting with Neptune's magnetic field. To confirm this discovery, researchers compare the recorded luminosity variations with solar wind measurements taken near Earth. They rely on data from stations monitoring the speed, density, and composition of the solar flux continuously. By cross-referencing the observations, they find that when a stronger impulse is recorded, a more intense glow appears on Neptune a few days or weeks later, depending on the particle travel time. Clearly and measurably, the James Webb shows that solar activity, despite being billions of kilometers away, still influences the chemistry of the distant blue giant's upper atmosphere. A long-awaited confirmation that draws a direct link between our star and one of the most distant planets in its array. But the challenge goes beyond the simple light show. These observations also disrupt our understanding of Neptune's internal magnetic field. During its flyby in 1989, the Voyager 2 probe revealed an inclination of about 29 degrees between the magnetic axis and the planet's rotation, with a field center offset by several thousand kilometers or miles. More recent analyses refine this figure to 46 degrees, according to some models, an extreme inclination that complicates interaction with the solar wind. The magnetic field lines are distributed asymmetrically, making each new measurement valuable. The detection of infrared auroras provides concrete elements to decipher the structure and movements of this invisible field. When the telescope captures these emissions, it doesn't just take a simple image. Thanks to its spectrograph, it breaks down the light into a fine spectrum, revealing the signatures specific to each gas or ion. The variations in intensity according to polar latitude and longitude give clues about the direction and power of the magnetic field. If an aurora appears in a slightly off-center area relative to the pole, this indicates a local convergence of field lines, thereby revealing the true orientation of the magnetic dipole, a method already proven with Jupiter, but achieves unprecedented precision in the study of Neptune here. An essential point lies in the very nature of the trihydrogen ion, considered the most reliable tracer of the aurora. Molecular hydrogen, ubiquitous in Neptune's upper atmosphere, is struck by solar particles. Under the impact, some atoms lose an electron and combine with a neighbor to form the ion responsible for the detected infrared radiation. Scientists are also monitoring other elements such as ionized helium or radicals from photolysis, but none are as revealing as this ion for tracking the influence of the solar wind. In the days following, excitement grips astrophysicists worldwide. Three-dimensional models map the auroras over Neptune's poles, while other teams simulate the circulation of electric currents within its magnetosphere. These currents, called magnetohydrodynamic, draw a network of moving energies that contribute to shaping the luminous arcs. Initial analyses suggest that the extreme inclination of 46 degrees might explain the mobility of the auroras, which sometimes seem to move. The magnetic lines change orientation unusually, possibly drawing sinuous patterns, even more intense luminous rings in certain regions. This scientific advancement fuels reflections on the planet's internal structure. As of today, the origin of such an inclined and offset magnetic field remains mysterious. Some researchers suggest the presence, deep down, of a moving ocean composed of water and ammonia that generates electric currents. Thanks to data from James Webb and the detection of infrared auroras, it's becoming possible to understand these hidden dynamics better. These results also provide insights into the planet's internal rotation, a parameter still not well understood. Since the magnetic flows align with the rotation axis, refining the magnetic field mapping lets us better estimate the real duration of a day on Neptune, a topic debated for several decades. These observations also represent a turning point for future missions. The confirmation of polar auroras strengthens the interest in a thorough exploration of Neptune and its magnetosphere, whose behavior differs significantly from other giants. This could also enlighten our understanding of exoplanets, many sharing Neptune's size. These distant worlds, often classified among the mini-Neptunes, sometimes orbit far enough from their star to develop surprising auroras linked to their own stellar wind. Studying our Neptune could thus be a key to understanding these foreign planets. From now on, the existence of polar auroras on Neptune is no longer a matter of speculation. It is a verified fact, demonstrated by the technical prowess of the James Webb Telescope and its infrared spectrograph. These lights revealed in the infrared trace a vibrant interaction between the solar wind and the blue giant's atmosphere. April 2025 thus marks a turning point for the study of distant planets and their magnetic fields. This long-awaited moment opens a new era in understanding Neptune, its unique magnetic tilt, and the secrets it holds beneath its icy clouds. Thanks to the piercing gaze of the telescope, humanity can better glimpse the intimate mechanics of the solar fringes, where the silence of space still resonates with the dancing lights echoing the sun. In 2025, observatories worldwide are directing their instruments toward distant Neptune to better understand the dynamics of its storms, a puzzle that has captivated astronomers for decades. As the eighth planet of the solar system, Neptune becomes a true laboratory for studying extreme atmospheric movements. Thanks to images collected by space telescopes and terrestrial radio telescope networks, scientists observe immense swirling structures known as vortices. Some, larger than Earth, evolve through the atmosphere, sometimes producing bright clouds visible on the surface. These luminous formations, though discrete to an untrained eye, provide specialists with crucial clues about the complex mechanisms of Neptunian meteorology. To understand the evolution of these whirlwinds, often identified as dark spots in high-resolution images, one must first look into the composition of Neptune's atmosphere. Although classified among the icy giants, this planet is primarily composed of dihydrogen, helium, and methane. The latter, composed of one carbon atom linked to 4 hydrogen atoms, condenses in the upper atmospheric layers when temperatures drop below 200 degrees Celsius, or 328 degrees. At these altitudes, the extreme cold, often near minus 210 degrees or 346 degrees, instantly freezes methane vapor, thus forming the crystals that make up the bright clouds detected from Earth or orbit. Analyses conducted this year show that some storms evolve rapidly. Their size can decrease by half in less than 12 months, while others maintain their extent for almost 2 years before dissipating. On average, the lifespan of these vortices is estimated to be less than 6 years. This assessment comes from rigorous monitoring conducted from several observation sites around the globe, where scientists record their trajectory, rotation speed, and contrast compared to the atmospheric background. It is now established that these systems appear, move, and eventually disintegrate or fragment into smaller structures, often absorbed by other clouds. To visualize the phenomenon, one can imagine an immense gaseous wheel rotating on Neptune. At its center, the pressure is slightly higher than around it, forming the heart of the vortex. As the winds intensify, the storm develops a well-defined border where the air moves either up or down. On Neptune, these upward movements give birth to the brightest clouds. These are composed of frozen methane crystals, which vividly reflect solar light, although weak at this distance. This association between convection and the formation of brilliant clouds has proven essential in recent observations. Researchers have also found that storms accompanied by the largest luminous clouds are also those showing the most active convection at altitude. For these clouds to form, methane must be transported from the lower layers to the colder zones where it condenses into crystals. Once frozen, these crystals reflect light and form very visible spots in the optical spectrum. This contrast with Neptune's deep blue background makes it easy to spot areas of strong meteorological activity. This process relies on a well-known mechanism. When gas rises in an atmosphere, its pressure and temperature decrease. On Neptune, this cooling accelerates the condensation of methane. The appearance of bright clouds thus follows the intensification of a vortex. A few days or weeks after the strengthening begins, cloud caps form. Their brightness varies depending on wind speed and temperature differences. The more intense the storm, the more light is reflected by the clouds, making it an excellent indicator of the energy involved. Data collected in 2025 reveals a major factor in the genesis and behavior of these storms: the heat exchange from Neptune's internal layers. Despite its distance from the Sun, the planet produces its own heat, originating from a slow release of energy accumulated since its formation. This heat locally warms certain areas of the atmosphere and causes temperature differences that fuel convective movements. Thus, the dynamics of Neptune's atmosphere depend as much on this internal energy as on solar input, which is minimal at this distance. Some vortices, over the course of their evolution, merge with others to form a larger system. During these mergers, winds can intensify greatly, causing localized storm phenomena. Conversely, vortices sometimes break when they encounter opposing winds at other latitudes. They then fragment into more unstable structures. This latitudinal mobility results from the banded organization of Neptune's atmosphere, similar to that observed on Jupiter or Saturn, where high-altitude currents circulate at high speeds. Observations show that in less than 6 years, a medium storm can travel several thousand kilometers or miles in latitude, reach nearly 5,000 kilometers or about 3,107 miles in diameter, and then suddenly disappear, leaving behind diffuse clouds with low brightness. Current campaigns supported by space agencies and capable amateur observers highlight the importance of tracking a storm throughout its life cycle, from birth, expansion, maturity to decline, to better understand these phenomena. The strength of the vortices is not measured solely by their size or longevity. Internal winds can exceed 2,000 kilometers per hour, or about 1,243 miles per hour, a record within the solar system. This speed is explained by Neptune's rapid rotation, completing a full turn in 16 hours, but also by the thermal differences between different atmospheric layers. This dynamic favors the creation of jet streams that amplify the vortices. Neptune's powerful and inclined magnetic field, though still difficult to model accurately, could also play a subtle role in these movements. By cross-referencing this data, researchers develop a coherent framework. Internal heating causes a rise of gas, which transports methane to the cold altitudes. There, it condenses, strengthening the storm. The more intense it becomes, the faster convection accelerates, generating even brighter clouds. As long as the supply of gas and energy is maintained, the structure can persist. But with the slightest thermal change or interaction with another system, it declines, sometimes giving birth to new phenomena. The estimation of a life cycle of less than 6 years is based on the analysis of visual and infrared signatures collected by a wide array of instruments. Ground-based telescopes observe specific wavelengths of cloud light, while satellites monitor thermal variations. This information is then integrated into atmospheric models to understand temperature and pressure changes in the studied area. Initial conclusions show that these vortices, subjected to perpetually changing conditions, struggle to survive longer when the environment becomes less favorable. The year 2025 thus marks a turning point in the study of Neptune's storms. It is now known that these vortices vary rapidly in size, often disappear or transform, and that the presence of bright clouds formed of methane crystals is a key indicator of convective activity. By locating these bright patches, astronomers can monitor almost in real time the internal workings of these structures. The more extensive and bright the clouds are, the more intense the methane ascent is, a sign of powerful meteorological activity. This assessment underscores how giant planets serve as unique laboratories to test our atmospheric models. Even though certain phenomena like storms or strong winds also occur on Earth, the scale and extreme conditions of Neptune offer an unparalleled point of comparison. Studying these storms, which sometimes last several years, enlightens us on how energy is transported, released, and recycled in the atmosphere of a distant world. It's a valuable avenue for understanding similar dynamics on other planets, including exoplanets with dense, icy atmospheres. In light of the advances of 2025, the link between the size variation of vortices and limited lifespan becomes evident. This time span corresponds to what is necessary to witness the entire cycle of a storm. Concurrently, the now well-established association between bright clouds and rising methane reveals the internal processes at work. Scientists hope that upcoming space missions dedicated to Neptune will deepen our understanding and unveil the secrets of these majestic whirlwinds in this distant world, as enigmatic as it is fascinating. Since the year 2023, the scientific community has been intensely working on new, large-scale projects aimed at exploring Neptune, the farthest planet in the solar system. Two major concepts are emerging, supported by the American Space Agency, in the hope of replicating the feat of the Voyager 2 spacecraft, the only one to have closely flown by Neptune in 1989. Between 2023 and 2026, teams are focused on precisely defining these missions, their feasibility, trajectories, and scientific objectives. Two approaches then take shape: the Trident mission, a finalist in the Discovery program, and Neptune Odyssey, a flagship-class project. Trident proposes a targeted flyby of Triton, Neptune's largest moon, whose composition has fascinated astrophysicists for decades. One of the strong points of the project is based on a captivating hypothesis: the possible existence of an ocean beneath its icy surface. This moon, with its retrograde orbit and active geysers observed by Voyager 2, seems to hide intense internal activity. From 2023 to 2026, engineers are working on the design of the spacecraft and the instruments to be on board. The flyby of Triton is scheduled for around 2038. Trident aims to collect unprecedented data on the surface and accurately map the topography of this enigmatic moon. The exchanges between a possible underground sea and the icy crust are of particular interest because they could offer conditions conducive to the appearance of rudimentary life forms. During the preparatory phase, teams are evaluating long-distance communication capabilities, resistance to radiation, and the energy needs for this long journey. While Trident focuses on Triton, Neptune Odyssey aims for a comprehensive exploration of the Neptune system. This flagship-type mission plans to send an orbiter around Neptune, accompanied by an atmospheric probe. According to the directions of the Decadal Survey of 2023, this project is among the major priorities for the upcoming decade. The objective: to unveil the mysteries of Neptune's internal structure, atmosphere, and magnetosphere. If approved between 2023 and 2026, Neptune Odyssey will include an orbiter tasked with mapping the rings, analyzing the weather, and tracking storms. The atmospheric probe, for its part, will dive into the planet's upper layers to measure pressure, temperature, and chemical composition. It will test instruments designed to withstand extreme winds and frigid temperatures in order to reveal the deep mechanisms of an icy giant planet. The competition for funding is fierce, with many space programs vying for attention. With this in mind, the Trident and Neptune Odyssey teams must, between 2023 and 2026, refine their scientific and technical justifications. Trident offers the prospect of a unique and rapid flyby of Triton, rich in potential discoveries. Neptune Odyssey, on the other hand, plans for a prolonged presence in the Neptune system, with long-term observations. Each of these strategies presents major strengths, and the debate promises to be lively. Beyond scientific issues, the question of the launch is central. The teams plan to use the gravitational assist from Jupiter, a method that allows for shortening the journey while saving fuel. The ideal launch windows are between 2030 and 2034, when Jupiter is strategically positioned between Earth and Neptune. These configurations facilitate a faster journey to the outer reaches of the solar system. Between 2024 and 2025, scientists will study different propulsion methods. Alongside the classic chemical engines, some advocate for electric technologies like ion propulsion, capable of optimizing the onboard mass and extending the mission duration. These systems require a reliable energy source, such as a nuclear generator, which complicates the technical complexity. These choices directly influence the design of the spacecraft and the selection of scientific instruments. During this same period, engineers will need to resolve the issue of interplanetary communications. At such a distance, transmitting data requires powerful antennas and high bandwidth. Neptune Odyssey plans for a network in the X-band, supplemented with higher frequency technologies to speed up exchanges. The distance from the Sun limiting available energy, The onboard systems will need to be powered by nuclear devices, essential to ensure the functioning of all scientific equipment. Another major challenge: protection against interplanetary debris and dust. Although the risks of collision with large objects are low, the impact of high-velocity particles can damage instruments. Designers are considering specific shields or even avoidance maneuvers. Thermal simulations are also being conducted to ensure that the orbiter will withstand the extreme temperatures that prevail near Neptune in an environment where sunlight is almost absent. All these parameters will be closely examined between 2023 and 2026 to build a solid mission plan. From 2026 to 2040, the exploration of Neptune is set to reach a new milestone. Major space agencies are planning ambitious missions to uncover the secrets of the blue planet and its environment. Thanks to recent technological advances, sending small miniaturized satellites capable of operating in extreme conditions becomes a concrete option. This dynamic promises to reveal unknown aspects of Neptune's structure and composition. One of the major axes is based on a constellation of CubeSats designed to map in 3 dimensions the arcs present in Neptune's rings. Long shrouded in mystery, these circular segments could be far more complex than imagined. Equipped with high-precision sensors and autonomous communication systems, these satellites would measure particle density and structural variations in space. The data collected will help to understand the mechanisms that shape and modify these formations in the spatial void. At the same time, a sub-terahertz spectrometer could be deployed to analyze Triton, Neptune's largest moon. By capturing electromagnetic emissions at very low frequencies, this instrument would make it possible to identify different internal layers and perhaps detect an ocean buried beneath the ice. Triton fascinates with its icy surface, which may contain clues to internal geological activity. Probing its structure would shed valuable light on the nature of icy moons and their potential habitability conditions. Interest in Neptune goes beyond the boundaries of the solar system. It represents a study model for better understanding the many mini-Neptunes spotted around distant stars. These planets, intermediate between Earth and gas giants, occupy a central place in exoplanet catalogs. Studying Neptune thus allows for better interpretation of the atmospheric characteristics of these yet inaccessible worlds. The TESS Space Telescope has already cataloged a large number of them. These planets display sizes and masses comparable to those of Neptune, but their internal diversity remains poorly understood. Some may harbor dense envelopes or extended liquid layers. By better understanding the peculiarities of Neptune, researchers hope to better grasp the physical properties of these newly discovered objects. The James Webb Telescope also plays a critical role. It offers fine spectral analysis of cold planets such as TOI 1231b. With exceptional sensitivity, it can detect minute variations in reflected light, providing crucial support to hypotheses built from observations made on Neptune. This planet thus becomes an essential reference for understanding these distant exoplanets. In this respect, Neptune stands out as a true natural laboratory. Its dense atmosphere, extreme distance, the subtlety of its rings, and the extreme physical conditions it harbors offer a unique framework for the study of ice giants. Each new observation, whether on dynamics or chemistry, enriches our understanding of planetary models. Yet many areas of uncertainty remain. Theories suggest the presence of superionic water at the core of the planet. Others question the formation and rapid disappearance of its gigantic vortices. Its magnetic field, highly tilted, leads to behaviors that are still poorly understood. The existence of auroras remains an intense subject of study, supported by ultraviolet observations. Between 2026 and 2040, several projects aim to clarify these phenomena. New launchers will enable sending more massive probes equipped with cutting-edge instruments. By using Jupiter's gravitational effect, trajectories can be shortened, facilitating the deployment of advanced scientific equipment. A large-scale collective effort will be necessary to meet these challenges. Various concepts are already emerging. Some propose sending an orbiter equipped with a module intended to analyze Neptune's atmosphere. Others bet on a mission dedicated to Triton, in search of signs of geological activity like geysers. Finally, the multiplication of CubeSats around the planet is gradually becoming a credible solution, driven by advances in miniaturization and space communication. The scale of the data collected will require sophisticated computer systems. Each spacecraft will generate a continuous flow of images, spectra, and measurements to process in real time. To manage these volumes, intelligent sorting algorithms and highly reliable interplanetary networks will have to be established. International scientific coordination will become essential to cross-reference, validate, and interpret the results. On the ground, major optical and infrared observatories, such as the Very Large Telescope or its European successor, will continuously monitor the evolution of Neptune and Triton. Their measurements will allow monitoring the appearance of cloud formations or vortices, complementing the data transmitted by the orbiting craft. This synergy will ensure a comprehensive view of ongoing phenomena. Researchers are also interested in the extreme temperatures prevailing on Neptune, close to -200 degrees Celsius or -328 degrees Fahrenheit, as well as its swift and tilted magnetic field. These factors raise many questions about internal movements, the stability of molecules, and the emergence of unexpected structures. These studies will impact the understanding of similar worlds elsewhere in the galaxy. From 2026 to 2040, a new era opens up for the exploration of Neptune. Between miniature satellites, state-of-the-art instruments, and large telescopes, the discoveries to come will not be limited to this planet. They will also help decipher the characteristics of the many similar planets identified outside the solar system. Neptune thus confirms its central role in the quest for unknown worlds. Among the most promising avenues, the study of superionic water remains crucial. Laboratory simulations show that under extreme pressure, water could adopt a state mixing fluidity and crystalline structure. The oxygen ions would form a stable base, while the hydrogen ions would circulate freely. This configuration could explain certain internal properties of Neptune and support new models of ice planets. Another major issue, understanding the origin of the gigantic vortices that torment the atmosphere. These systems reach impressive speeds, sometimes exceeding 600 meters per second, or approximately 1342 miles per hour. They seem to draw their energy from deep heat, a residue from the formation of the planet. This energy, rising up, would provoke a convection forming these lasting whirlwinds, capable of sustaining themselves for several years before disappearing or moving. Finally, the interaction of the Sun with Neptune's magnetosphere raises many questions. Its magnetic field, decentered and tilted, creates zones permeable to solar particles. This imbalance could be the origin of unique polar phenomena. Future observations on site, supported by high-definition ultraviolet images, will allow for a better understanding of the mechanisms shaping these luminous and dynamic manifestations.